Hey, so I've had a couple of questions asking me about why do filters behave the way they do. So I've had a couple of people asking me, do I need to memorise the configurations of filters and stuff for my exam? Well, the answer is that you can, but you should understand what's going on underneath this, and that's why I'm going to explain it here. So the way filters behave is all down to the nature of inductors and capacitors with changing frequency. The thing is that they're opposite, so that's why if you replace an inductor with a capacitor, you get an opposite kind of filter because they're opposite components. So here I've got a capacitor, and I've just drawn my circuit, but obviously, you know, it's a capacitor. At low frequencies, capacitors behave as open circuits. That's just something that you need to live with, really. And at high frequency, they behave like short circuits. These are assumptions that we're making, and by making these assumptions, we can analyse the behaviour of more complex circuits using these components. So personally, I've just memorised what the behaviour of a capacitor is, and then I know that an inductor is the opposite. So let's look at the inductor. Let's just unravel it. So here's our inductor, and it's completely opposite case. So here, at low frequency, it behaves as a short circuit, and at high frequencies, it behaves as an open circuit. So we just zoom out a bit. There's our two circuit components, and they are opposite to each other. So that's what we use to evaluate our our filter circuits. So here's an example. This is just a low-pass filter that I'm going to use. So this is the configuration where the voltage input is applied over these two terminals, and then the output is read across these two terminals, and we've got a resistor and a capacitor in this configuration. For an inductor, you can do exactly the same procedure that I'm going to do, it's just the components will obviously be different, and the other filter configurations, they'll be in different positions. The principle is exactly the same. So what I'm going to do, I'm going to look at what this circuit does at low frequency and then at high frequency, and this will confirm that the filter is going to behave as we expect it to behave. I'm trying to cover stuff up just because it's a bit less confusing to have too much information. So at low frequencies, we're going to make the assumption that our capacitor behaves like an open circuit. So what I've done is I've just redrawn my circuit, and instead of having a capacitor, I've got an open circuit. So I've still got the input applied here and the output applied here, and the resistor stays where it is. And what we can see, because this is an open circuit, what we're actually going to see is that the output is going to be more or less equal to the input. So basically there's no attenuation at low frequencies. And since that's a low pass filter, that's good, because it means what you put in at low frequencies will be what you get out. That's what we like to see. So what happens when we go to high frequency? Well, this time we're going to replace our capacitor with a short circuit, because that's our assumption that at high frequencies it behaves like a short circuit. So that's what I've done here. I'm still applying the input over these terminals, the output over these terminals, and the resistor stays the same. So this time you can see this is actually effectively short-circuited. So what we're going to get at high frequencies, because our capacitor is acting as a short circuit, is we're going to get our output is approximately 0, because that means there's no output at high frequencies, because this is all short-circuited. So if you imagine a more simple configuration, this is just cancelling, so you'll get 0 output. So what the conclusion is that at low frequencies we get an output approximately equal to our input, and at high frequencies we get an output approximately equal to 0. So that's what a low-pass filter does. It allows low frequencies to pass and stops high frequencies. So that's what it's doing, and that's the rationale behind why filters behave the way they do.